Hey everyone, and welcome back. Today we're going to be exploring some things called factoring strategies that are very important for a variety of different math concepts, ranging from basic algebra, calculus, differential equations, linear algebra, and so on. So what I want to do is step through 9 different factoring strategies that everyone definitely should have before pursuing higher level mathematics. So what I want to do is just start off with the easier types and then move up to the more complex types. So the first method that you definitely should know is referred to as the greatest common factor approach. Some people also abbreviate this by the GCF approach. So let's illustrate this method with a couple examples. So example 1, x cubed minus x squared. So what do we mean by factor an expression? So when we say factor an expression, we would like to break this expression up into a product of smaller complex expressions. So for this particular example, we have a cubic minus a quadratic term. So if we can represent it as a linear times a linear times a linear term, that would be a factored expression. But sometimes you cannot factor it, and we just say it's non-reducible, whatever that means. So in this case, notice that we can write this as x times x times x minus x times x. Notice that there's two x's in both of these terms. I can also write times 1 just in case I don't want to forget that a 1 is still there. So if I factor out two x's, which is just the same thing as x squared, I'm going to get x squared times x left over from the first, and then 1 left over from the second. So I'm going to have x minus 1 there. So this is going to be my factored expression of x cubed minus x squared. Now, you could write this as x times x minus 1, but in some sense, x times x is x squared, so you don't really get anything new out of that particular expression, so most people will just prefer this first expression as the factored answer. So example 2. Suppose we have 6x plus 18. Notice that we only have x in the first term and no x's in the second term, so the only thing we're going to be looking for here is a numeric greatest common factor. Notice that I can write this as 6x plus 6 times 3. Notice that I'm going to have a 6 in both the first and the second term, so I can write this as 6 times x plus 3. So that is going to be my factored expression. And let's combine these two different things together. Let's assume we have 4x squared minus 2x cubed, and we're asked to factor this expression. Notice that I can write this again as 2 times x minus 2 times x times x times x. Notice that I have a 2 in both of these expressions. I have two x's in both of these expressions. So if I factor them out, I'm going to have 2x squared. I'm going to be left with 2 in the first term and x in the second term. So I'm going to be left with 2 minus x inside of the parentheses, and of course you can write those in front as parentheses terms as well, but this is the factored representation of the original problem. So sometimes expressions might not be easily factorable, at least via greatest common factors. So the second method that you definitely should be aware of is called the difference of squares. So before I do a couple examples, I actually want to sort of derive where the difference of squares method comes from. So what I'm going to look at is the expression a plus b times a minus b, where a minus b are some numbers or potentially some expressions. So if I distribute this out, what will I get? So I'm going to have a times a, which is a squared, a times b, which is minus ab, b times a, which is just ba, and b times minus b, which is just minus b squared. Notice that AB and BA are just opposites of each other because real numbers are commutative, so these things are going to cancel out, and we're just going to be left with a squared minus b squared. In terms of the name, difference means subtraction, and then we have two different things squared. In particular, it's the same things that were in the original expression, something plus something times something minus something else. So if you see an expression that is just something squared minus something else squared, you can directly represent it as that something plus something else times something minus something else. So let us look at a couple examples just to illustrate the difference of squares method. Suppose I have x squared minus 9 and we're asked to factor. Notice that we do not have a greatest common factor in the first and second term. The first only has x's and the second only has 9's. So the greatest you can factor out of these is 1, but that doesn't really change much. But we can notice that this is the same as something squared minus something else squared. So therefore, this is a difference of squares. Therefore, this is going to be equal to x plus 3 times x minus 3. And you can FOIL or distribute that out and verify that it's going to give you x squared minus 9. So we've turned this quadratic expression into a product of linear expressions. Let's look at a couple other examples. So let's just assume we have 4x squared minus 25y squared. And again, we're going to see if something squared is equal to this and something squared is equal to that. Notice that 2 squared is equal to 4 and x squared is equal to x squared. Therefore, 2x the quantity squared is the same as 4x squared. Similarly, 5 squared is 25 and y squared is y squared. Therefore, 5y the quantity squared is 25y squared. So we have something squared minus something else squared, so this is indeed a difference of squares. Therefore, this is just going to factor into 2x plus 5y times 2x minus 5y. Let's look at one that might not look so obvious at first. Example 3. Suppose I have x squared minus 10. So it's very clear that x, the quantity squared, is going to give us x squared. Now, what squared gives us 10? So if you're very clever, you might remember that the square root of 10 times the square root of 10 is the same thing as 10, so the square root of 10 squared will be equal to 10. So if you're familiar with radicals and this useful property, therefore even if that is not a perfect square, you still should be able to factor it. So that means this is just going to be equal to x plus the square root of 10 times x minus the square root of 10. And that's how to do difference of squares. The next method is very similar to the difference of squares, and this is called the method of the sum of squares. Sum of squares. So instead of differences, it's sums. Let's start off by motivating it. So let us define firstly that I is equal to the square root of negative 1, so this is our complex unit, and let's consider the expression a plus bi times a minus bi. In particular, a number times its conjugate. So once we FOIL this, what will we get? So we're going to have a squared minus abi, and then plus abi, and then we're going to have minus b squared I squared. Keep in mind, if I is equal to 2, the square root of negative 1, that means I squared will be equal to minus 1. So that means this is just equal to a squared, those two cancel. That's just equal to negative 1, which is going to turn that minus into a plus. So we're just going to be left with a squared plus b squared, which is the sum of two things squared. Therefore, if you see the sum of two things squared, you can always represent it as the product of these two conjugate exponential linear factors. Let's look at a couple examples to illustrate this method. Example 1. Suppose I have x squared plus 4, which we already know is just going to be x squared plus 2 squared. So this is the sum of squares, therefore we can factor it over the set of complex numbers, in particular x plus 2i times x minus 2i, and that's all. Example 2. Suppose I have x squared plus 7. So what squared gives us 7? Well, it's not a pretty number, but it does have a name. It's the square root of 7. So since we have a sum of two squares again, we can factor this as just x plus the square root of 7i, and then x minus the square root of 7i. Let's look at another example that's quite fun. Example 3, x to the fourth minus y to the fourth. So we can write this as x squared squared minus y squared squared. So this right here is just a difference of squares. So that means this can factor into x squared plus y squared and x squared minus y squared. Now we're not done yet. It might still be able to be factored. Notice we have degree 4, degree 4. Now we have our product of degree 2's. Maybe we can break this down in degree 1's. Notice that here we have a sum of squares, and here we have a difference of squares, and we already know how to factor those. So what will our final factored answer be? So x squared plus y squared is our sum of squares, so it's going to be x plus yi times x minus yi for our sum of squares. And then we're going to have x plus y times x minus y for our difference of squares. So our degree 4 has now factored into 4 degree 1s. And that's how you use the difference of squares, sum of squares, and also the greatest common factor methods. The next method that we're going to introduce is known as the method of monic trinomials. So trinomials usually means 3 terms. So what we're going to be looking at in particular is second degree, I guess I should put that there. So second degree monic trinomials, so polynomials of the second degree with leading coefficient 1. So that's practically what monic means. So leading coefficient 1. So that's actually going to make things a little bit nice for us. So we're going to be looking at things of the form x squared plus some number beta x plus some other number, let's call it gamma. So how to factor this expression? So let's assume that this factors into the expression x plus a times x plus b. So that's going to be our answer. Our only question is, what is a and b going to be equal to? And how are we going to find them from these numbers beta and gamma? So if we FOIL this right-hand side, we're going to have x squared plus bx plus ax plus ab. And if we greatest common factor those middle two terms, what we're going to have is we're going to have x squared plus a plus bx plus ab. So if we analyze these two equations, so we have x squared plus a to beta x plus gamma, and x squared plus a plus b x plus a times b, we can equate like coefficients for this expression. So notice that the front coefficient for x squared is 1 in both of these terms. And then we have that beta and a plus b are going to be the same, right? So we need two numbers a and b such that a plus b is equal to the number in front of x, and a times b is the number by itself. Once we can guess or construct these two numbers, then those are going to be our answers. So practically what we have here is a system of nonlinear equations, which are always fun to solve generally speaking, where beta and gamma are known, and a plus b are our unknowns. So let's look at a couple examples where guessing these numbers a and b are actually quite easy. So example 1. Suppose we have x squared plus 8x plus 12. So what we're going to be looking for is two numbers that multiply together to give us 12 and add together to give us 8. So what numbers do that? So 12 we know can break down into 12 times 1. We can also do 6 times 2. We can also do 4 times 3, and all of the mirror images, at least of the set of integers. And if we notice that if we look at 6 and 2, 6 plus 2 is equal to 8, which is the number in front of x. Therefore, 6 times 2 is 12, and 6 plus 2 is 8. Therefore, 6 and 2 are the numbers that we want. Therefore, our factorization is going to be x plus 6 times x plus 2. And you can FOIL that just to make sure that you're correct. Example 2. Suppose we have x squared minus 12x plus 36. Again, we're looking for two numbers that multiply together to give us positive 36 and adds together to give us negative 12. So let's look at the factorization of 36 and see if the numbers are nice. So 36 can break down into 36 times 1. We also have 18 times 2. We have 12 times 3. We have 9 times 4. And we have 6 times 6, and all of the mirror images. Now keep in mind, the way we can get 36 is either a positive times a positive or a negative times a negative. And we need to be able to add to get a negative number in front of x. And if we add two numbers that are positive, you can't get a positive number. Therefore, the numbers that we're going to be looking for are both going to be negative. So that means we can put a negative sign in front of these to see which one is going to generate what we want. So negative 36 plus negative 1 is just going to be minus 37. That's going to give us minus 20. That's going to give us minus 15. And minus 9 plus minus 4 is minus 13. And minus 6 plus minus 6 is minus 12. Aha. So those are our characters. So minus 6 and minus 6 are our numbers. Therefore, the factorization is going to be equal to x minus 6 times x minus 6 as their factorization. And some people will even write this as x minus 6, the quantity squared, because that's just something times itself, which is this. And just as a side note, keep in mind that this is not the same as x squared minus 6 squared, because that would factor into x plus 6 times x minus 6, which is not the same thing as x minus 6 times x minus 6. So make sure you don't verify it in the wrong way. But that is going to be your factorization of the original monic trinomial. Let's look at one more. So example 3. X squared minus 3x minus 28. So how am I going to get 28 in terms of a product? So 28 can be represented as 28 times 1. We also have 14 times 2. And we also have 7 times 4. Our product is negative, so it's going to be a positive times a negative number. So we can either do positive 28 or negative 1, positive 14, and negative 2, positive 7, or negative 4, or the reversals, right? So if one is positive, the other has to be negative. So if you sort of think about how we can get that, 28 minus 1 and negative 28 plus 1, 14 minus 2 or negative 14 plus 2, 7 minus 4 or negative 7 plus 4, well, negative 7 plus positive 4 is going to generate minus 3, so those are going to be our numbers. So we clearly see that this is going to factor into x minus 7, x plus 4, and again, if you're not comfortable with factoring, definitely FOIL these out just to make sure you have the right factors. So monic trinomials are nice, but in some sense, the problems need to be constructed in a particular way so that those numbers that we're looking for, a and b, are integer factors of that last number. Or do we really even need that nice property? Moreover, what if these numbers that it does factor into aren't really nice at all? Square roots, complex numbers, or even fractions. Can you still factor it? The answer actually is yes. So the next method will address this issue. And this method is called completing the square, which is quite nice in a lot of circumstances and applications in higher math. So let's look at our particular example, at least for monic trinomials. We'll deal with the non-monic a little bit later. So what we have here, let's look at x plus a, the quantity squared, which is a very nice factored answer. In particular, that's just x plus a times itself. This is going to factor into x squared plus 2ax plus a squared. So if we have an expression of this form where we have some number squared at the end, because we're trying to find what this number is, it's just that number divided by 2, and then we're going to square it to get that last number, right? So this is the magic number divided by 2. That's going to give us a, and then when we square it, we're going to have that number there. So if we look at a little example to sort of illustrate this observation, for example, x squared minus 10x plus 25, if we take that number divided by 2 and square it, notice that we have minus 5 squared, which is 25, which is the number at the end. That means this factors nicely into x minus 5, the quantity squared. So now let us pretend that it's not so nice. So let's assume we have x squared plus 12x plus 22. So if we take this number in front of x divided by 2 and square it, we're going to have 12 divided by 2, the quantity squared, which is going to be equal to 36, which is not that number there. But what we can do is we can put it there anyway. In particular, we're going to do it this way. X squared plus 12x, we're going to add 36 and then subtract 36. And don't forget the 22 that used to be there. So all I've done is just I've added 0, which we should already know doesn't really change our expression. But what's interesting is that the first piece of this is actually pretty nice, because we know that that's just going to be x plus 6, the quantity squared, and then minus 36 plus 22 is just the same thing as minus 14. Now what we have is we have something squared minus something else squared. So this is just a difference of squares, so we should be able to solve this expression. In particular, this is going to be equal to x plus 6 plus the square root of 14, and then x plus 6 minus the square root of 14, and this is going to be the factored representation of x plus the 12x plus 22 factored into two linear factors, where these numbers, 6 plus the square root of 14 and 6 minus the square root of 14, are subjectively not as nice as the other examples that were given. Let's look at another example, because this is very, very useful. Let's assume we have x squared minus 4x plus 7. So I'm going to take the number in front of x, divided by 2, and square it. So negative 4 divided by 2 is minus 2, and minus 2 squared is going to be 4. So I'm going to write this as x squared minus 4x plus this magic number that I've found, then subtract it, and don't forget your lonely little 7 that used to be there. So this x squared minus 4x plus 4 will factor into just x minus 2 squared, and then we're going to have minus 4 plus 7, which we know is just positive 3. So we know that this is just x minus 2 squared plus the square root of 3 squared, which is just a sum of squares, which we know can factor over the set of complex numbers. So this is going to be equal to x minus 2 plus the square root of 3i, and then x minus 2 minus the square root of 3i, and that will be the factored representation of x squared minus 4x plus 7. Since this method can come off as a little bit intimidating, let's just do a couple more examples that are, I don't know, maybe a little bit more difficult, just because of the numbers that generate. So example number 4. X squared plus 5x plus 2. Notice here that the number in front of x is an even, so we're definitely going to have some fractions here. No matter, the number that we're going to be looking for is the number in front of x divided by 2 squared, which we know is going to be 25 fourths. So this is going to be equal to x squared plus 5x plus 25 fourths minus 25 fourths, and then we're going to have this 2 at the end. And keep in mind, 2 is the same as 4 over 4. We're going to need that once we combine these numbers at the end. No matter. So we have x squared plus 5x plus 25 over 4. So what two numbers multiplies together to give you 25 fourths and adds together to give you 5? You might think about it a little bit, but the number is right here inside this parenthesis. In particular, 5 halves plus 5 halves, so half of 5 plus half of 5 is equal to a whole of 5, and 5 halves times 5 halves is 25 fourths. So this is going to be equal to x plus 5 over 2, the quantity squared, and then we're going to have minus 25 plus 4, which we know is just going to be equal to, what is that? So multiply that by 2, so 2 times 4 is going to be equal to 8, so minus 25 minus 8 will be equal to, what is that, 17 fourths. So this is just a difference of squares, so let's just write it in that form, so x plus 5 halves, and then minus, so that's going to be the square root of 17 over 2 squared. Once we have it in that form, it's pretty obvious. So this factors into x plus 5 over 2 plus the square root of 17 over 2, and x plus 5 over 2 minus the square root of 17 over 2, and that comes from the difference of squares relationship. Now let's look at an example where it's not a monic trinomial. This is where the math can get really, really exciting. So let's look at 2x squared plus 7x minus 15. So what I'm going to do is I'm going to begin by factoring out that 2, even if these are not even, or even if those are not factors of that number in front of x squared. So once I do that, I'm going to have 2 times x squared plus 7 halves x minus 15 halves. Now what I'm going to do is I'm going to factor this just like I did before. So there's my number in front of x, so that means that number in front of x divided by 2 squared, which is the same as 7 fourths squared, which you know is 49 over 16, right? So this is going to be equal to 2 times x squared plus 7 halves x plus 49 over 16 minus 49 over 16 minus 15 over 2 times 8 times 8 to get a common denominator for those last two terms. And now I'm going to factor this first three terms out. So once I do that, that's going to be equal to what? So that's going to be equal to x plus two numbers that multiply to give us 49/16 and add together to give us 7/2. That's the number that was inside of our parentheses before, which was just 7/4 squared. And over here we have minus 49 minus 15 times 8, which is going to come out to minus 169 over 16. Right? And keep in mind that is just the same thing as 13 over 4, the quantity squared. So we can just go ahead and factor this out. So this is going to be equal to 2 times x plus 7 over 4. Again, this is just a difference of squares. So x plus 7 over 4 minus 13 over 4 as 1. And then x plus 7 over 4 plus 13 over 4 as the second. And this is just going to be equal to 2 times, so 7 plus 13, that last one is actually quite nice. That's just x plus 20 over 4, which is x plus 5. And then we have 7 minus 13, which is just going to be equal to minus 3 over 2. Right? So I can remove these brackets since they don't really have any relevance anymore. So I can write this as 2 times x minus 3 over 2 times x plus 5. And I can distribute this 2 into one of these factors, and I'm going to factor it into this one. So I'm going to write that as 2x minus 3 times x plus 5. Now notice that these numbers are actually quite nice. There is another method that you could have used to generate this answer. So let us go ahead and look at how that method works. But notice that even though this was complicated, it's sometimes necessary, especially if that number was not nice. If that number does turn out to be some nice number, like a rational number, then you probably can solve this with another method, which is called the AC method, which comes next. But if it doesn't come out to a rational number, then this method, in some sense, is the only rational way to go about that irrational factorization. So the AC method can be viewed as a generalization of the monic trinomial method, where we are allowing the leading coefficient to not be 1. Now again, this does not always work, especially if you're aiming for pretty numbers, but if it doesn't work, you can always use the completing the square technique in order to factor. So let's look at the same exact example we did with the completing the square method and sort of see how the AC method can be applied. So we have 2x squared plus 7x, and then we had minus 15. So we call it the AC method is because we start off by multiplying a and c together. So a and c is equal to 2 times minus 15, which is equal to minus 30. Now we're going to be looking for two numbers that multiply together to give us minus 30 and adds together to give us 7. So let's look at that. So we're going to have 30 times 1, we're going to have 15 times 2, and we're going to have 10 and 3. The product is negative, so one of these has to be negative, and we're going to be adding to 7, so 10 plus minus 3 obviously is going to give us the 7 that we want. So once we find these two numbers, we're going to be decomposing the number 7 with that. So let's see what that means. So this is going to be equal to 2x squared. We're going to decompose 7 into 10x minus 3x, and don't forget your little 15. And then what we're going to do is we're going to factor by grouping the first and second pairs. So in case you're sort of wondering, does this always work? If you can find these numbers, this will always lead to the correct answer. So the greatest common factor of 2x squared and 10x we know is going to be equal to 2x, leaving us with x plus 5. The greatest common factor of minus 3x and minus 15 will be equal to minus 3, leaving us again with x plus 5. Notice that x plus 5 and x plus 5 is a factor of both the first and second terms, so we can factor out x plus 5 of the first, leaving us with 2x, and x minus 5, x plus 5 out of the second term, just leaving us with minus 3, and that gives you the same exact answer as we generated with the completing the square technique. But if you cannot find those factors that generate to the sum of the middle, then completing the square would have to be used in that particular context. Let's look at another example to sort of practice on one where we don't know the answer to. So example 2. Suppose we have 6x squared plus x minus 2. So non-monic trinomial, so let's begin by multiplying a and c. So a times c will be equal to minus 12, and we need two numbers that multiply together to give us minus 12, and adds together to give us positive 1. So we have 12 and 1, we have 6 and 2, we have 4 and 3, and their mirror images. The product is negative, so one has to be positive, one has to be negative, and obviously 4 plus minus 3 will give us our 1, so 4 and negative 3 are our magic two numbers. So we're going to decompose 1x into positive 4x minus 3x minus 2, and then we're going to factor by grouping the first and second pair. So the greatest common factor for the first two will be 2x, leaving us with 3x plus 2. And the greatest common factor of minus 3x and minus 2 will be minus 1, leaving us with 3x plus 2. For this to work, if you found these numbers, these have to be the same. Once they are the same, observe that you can factor 3x plus 2 out of both, leaving us with 2x minus 1 in the first and second term, respectively. And that's how the AC method works. So the AC method we were using on trinomials, in particular quadratic trinomials, and within that factoring strategy was another factoring strategy where we grouped two terms together, grouped the other two terms together, and then performed some factoring strategy on them and hope for the best from there. Factoring by grouping typically is the name given to that, but we don't have to use it for quadratic trinomials. We can put it on things like this. So let's assume we have this degree 4, where we have x to the fourth, x squared minus 2x squared minus 2. Now you may think, oh, x squared and minus 2x squared can combine with each other. In particular, that's going to give us x squared minus x to the fourth minus x squared minus 2. And then you're like, well, how do I factor this particular thing? Well, we'll look at that in a moment. But if we sort of group the first two and the last two terms together, we actually might be able to solve this in this way via grouping. So if I GCF the first two, I'm going to have x squared times x squared plus 1. And if I take out a minus 2 out of the last two terms, notice that that's also going to give me x squared plus 1. The insides of those parentheses are the same, so this is just going to give me x squared minus 2 times x squared plus 1. Keep in mind that's just a difference of squares and a sum of squares, so technically I can write that as x plus the square root of 2, x minus the square root of 2, x plus 1i, and x minus 1i, and that's your completely factored representation. Now, is it possible that we can factor this? Notice that our x cubed and our x are missing, so it's similar to a quadratic. In particular, what we can do is we can let u be equal to x squared, so in some sense we're making a substitution here, and we're going to have u squared minus u minus 2. And then we're like, oh, that's just a monic trinomial, so we just need two numbers that multiply together to give us minus 2 and add together to give us negative 1. So we're like, okay, well, I know minus 2 plus 1 will give us minus 1, and minus 2 times positive 1 will give us minus 2. So that's our factored representation for u. Then we just switch back into the x squared. So we're just left with x squared minus 2 times x squared plus 1, which puts us right back into the place that we were. But sometimes when you combine like terms like this, sometimes the factorization of this new equation sometimes is not as obvious. Let's do an example where we have a couple variables floating around, like x and y, possibly some other things. But let's keep it simple. So 5xy minus 3x plus 25y minus 15. And let's assume that we want to group in the original grouping. Sometimes we might have to rearrange some of these terms to get a better grouping, but let's group in this particular order. So what can I take out of the first two terms? So notice that x is the only thing there, so I can get a 5y minus 3 for the first pairing. And for the second, I can factor out a 5, giving us 5y minus 3. And look, the insides are the same. That's great. Which means this is just going to factor into 5y minus 3 out of both, x in the first, 5 in the second. That is your factored representation, and that's practically how factor by grouping works. Now the next method focuses on degree 3, so this is method 8, I believe. And this is the sum, you can also call this method 9 too, but I'm going to combine them into one. The sum and difference of cubes, not squared. So one can show that if you take a plus b times a squared minus ab plus b squared and FOIL that out, you're just going to get a cubed plus b cubed. And if you take a minus b times a squared plus ab plus b squared and distribute that out, you're going to get a cubed minus b cubed. So if you see a sum or difference of two things cubed, we can always represent them in terms of these factored representations, the first being a linear expression and the second being a quadratic, which one can prove actually always factors over the complex plane, in particular always going to have an imaginary unit hanging out in those two linear factors when you break down that quadratic. But I won't get into the proof there, but you should have all the tools at this stage to sort of justify that. So let's look at a couple examples on how the difference of cubes and sum of cubes formulas work. So example 1. So x cubed minus 27. So what cubed gives us 27? So you should know that that's going to be equal to 3. So 3 times 3 is 9, and 9 times 3 is 27. So that means this is a difference of cubes. So using the difference of cubes relation, which is that last relation there, this is going to be equal to x minus 3 times x squared plus x times 3, which we can write as 3x, plus b squared, which is 3 squared, which we can write as 9. Right? And then we can possibly factor out over the complex, but I won't do that in this particular case. But anyway, that's how you do difference of cubes. Let's do the second, another one. Let's do x cubed plus 8. So what cubed gives us 8? You should know that that's going to be 2. So it's going to be x cubed plus 2 cubed. So this is a sum of cubes. So that's going to be equal to what? So that's going to be equal to x plus 2, x squared minus 2x plus 4. Always note that these two signs are always opposite, and those two signs are always going to be the same for the sum and difference of cubes relations. And the last one, always going to be a plus. Let's actually go ahead and factor this little x squared minus 2x plus 4 while we're at it, since we already know how. So that's going to be equal to what? X squared, x plus 2 times, so we're going to have some magic number, which is going to be minus 2 divided by 2, the quantity squared, which we can find to be equal to 1. So we're going to have x squared minus 2x plus 1 minus 1 plus 4. So we're going to factor that. So we're going to have x plus 2 times x minus 1 squared plus 3. And that is just a sum of squares, which we know factors over the complex, as we already mentioned before. So that means this is going to be equal to x plus 2 times x minus 1 plus the square root of 3i, and x minus 1 minus the square root of 3i, and that is the full factorization of x cubed plus 8. Isn't that nice? The last method that I want to introduce today is a method called the method of monic cubic polynomials. So what we're going to be looking at is cubic polynomials of the structure x cubed plus alpha x squared plus beta x plus gamma, right? Where alpha, beta, gamma are real numbers and the leading coefficient of this being 1. So is it possible to factor cubics provided that these numbers alpha, beta, gamma are nice? Let's assume that that is the case. There are other methods in case that alpha, beta, gamma are not nice, and you can solve generally any cubic, but we'll leave that for a later time. So let's assume that this thing does factor nicely into x plus a times x plus b and x plus c, and one can actually prove that there always exist these numbers a, b, and c in the set of complex numbers such that this is true, where sometimes at most 2 of these are complex numbers. It's possible that all 3 are real, but usually sometimes we have 1 real and 2 complex. but we'll get into that theory later. So if you distribute these three out very carefully, what you're going to have is x cubed plus a plus b plus c x squared plus ab plus ac plus bcx plus abc multiplied together, right? So it's very easy to analyze the product of things because we can usually decompose that into a prime factorization. And obviously identifying sums of numbers, that sort of goes back to our monic trinomial case. That probably is the second easiest thing to observe, but the number in front of x, that's usually the hardest to observe in terms of the numbers because you have three products all added together and there's so many variations that could actually take, right? But if you can identify three numbers that multiply together to give you this last term, and the sum of those three numbers is the number in front of x squared, and as long as you verify that AB plus AC plus BC is equal to the number in front of x, that means you have your numbers A, B, and C. That's going to factor into. So let's look at an example of how this works. So let's assume we have x cubed minus 4x squared plus x plus 6. So 6 is obviously the number that we're going to start focusing on, and we're going to try and decompose this. So let's assume we have 1, 1, and 6 as our product. There's several other products out there, but let's just focus on that one, right? So keep in mind the product of those has to be 6, and the sum of those has to be equal to minus 4. So is it possible that we can add to minus 4 from 1, 1, and 6? The answer should be yes, right? Well, maybe no, right? Because if we do, let's see, 1 plus 1, so if we do 1 plus minus 6, what is that going to be? This is going to be 2 plus negative 6, that's going to be equal to minus 4. So maybe 1, 1, negative 6 are our numbers. So let's give that a go. So if we do 1 times 1 plus 1 times minus 6 plus 1 times minus 6, that's going to give us 1 minus 6, which is minus 11. But that's not equal to 1, right? So that's definitely out, right? So this sequence almost works, but doesn't quite work. So we have to look for another product. So again, how can we get 6? Well, we can do 1, 2, and 3. So how can we add these with some minus signs to get a minus 4? So if you think a little bit, what you can do is you can do, let's see, how can we get minus 4 as a sum? So we can do like minus 1, minus 3, positive 2. What does that give us? That gives us minus 4 plus 2 is equal to minus 2. We could also do 1 minus 2 minus 3. That's minus 5 plus 1. Aha, there you are. There's our minus 4. Right? So now we need to verify that this sequence gives us what we want. So let's do that order. So 1 minus 2, 1 minus 3, minus 2 minus 3. So that's going to be equal to minus 2 plus minus 3 plus positive 6. So that's minus 5 plus positive 6, which is 1, which is the magic number that we want. So we found three numbers, 1 minus 2 minus 3, that multiplies together to give us 6, adds together to give us minus 4, and combinatorially multiplies and adds to give us 1. So we found our factors. So that means this thing will factor into x plus 1, x minus 2, x minus 3, and you can FOIL these out and see that it definitely does give us that original one. There are definitely several other advanced factoring methods, but they require a couple little clever tricks, which we'll definitely get to a little bit later. But for now, I hope you enjoyed this video, and I'll see you in the next one. Take care.